chapter 37, or do you have some pressing problems you might want to look at? Let's what, Sonny? You got something? Yeah, let's take a look at chapter 37 then. My other classes are taking the third test this week, so I'm a little behind, but I only plan 3 tests a week anyway. So. Last test might be taking might. Selected. One of these days I'm going to figure out how to do this.
Here we go.
Wave optics, chapter 37. Particle nature of light was the basis for ray or geometric optics, which is what we just looked at in chapter 36. But the wave nature of light is needed to explain some various phenomena that we observe with light. That is interference, diffraction, and polarization. These 3 things we're going to talk about in the next 2 chapters. Particular interference, light waves interfere with each other just like mechanical waves do. Electromagnetic fields that constitute the individual waves combine for either constructive or destructive interference. 2 conditions in order to have interference would be, 1, we'd have to have the sources maintain a constant phase with respect to each other. If they're out of phase, then all bets are off. So we want them to maintain a constant phase with respect to each other. Hence, we would say that they must be coherent. If they're in phase, they're coherent. And the waves must have identical wavelengths, which means they must be monochromatic. So we want the 2 sources to be coherent and monochromatic. To produce a coherent source, one method, the old method, is to pass light through a slit. So light from a monochromatic same source is allowed to pass through a narrow slit. Light from the single slit is allowed to fall on the screen containing 2 narrow slits themselves. The first slit is needed to ensure that the light that reaches the other 2 slits is coherent. In other words, you have one source producing the light that hits the 2 other slits, and hence you ensure that the light hitting those other 2 are in phase. a laser. Laser is coherent source. It's intense, in phase, monochromatic, same wavelength, over a width of several millimeters so that you can get two closely spaced slits. And hence laser light can be used as your source directly. But back in the old days, they didn't have lasers, so they used the single slit, double slit apparatus.
So this one come into play on the CD player would, isn't it?
Yeah, I mean, you would observe interference effects. In fact, interference effects are used for CD reading and DVD reading. Young's double slit experiment. Significance. This experiment gave the wave model some credibility because it's inconceivable that particles of light could cancel each other. So if you treat light as a particle, each of them being an energy bundle, then in physics it's inconceivable that just that bundle of energy could cancel out and you'd have nothing afterwards. So the wave model gives us a chance to look at that kind of effect. And Young's double slit experiment provides a method for measuring the wavelength of light. We'll see as we get our results here that there would be a relatively simple way to obtain the wavelength of the light from the interference pattern. Here's how it looks like. We have light incident on the screen from the first slit, call that the source S0. Light waves emerge from this slit, arrive at a second screen that contains two narrow slits, and we'll call that S1 and S2. Sources S1 and S2. So at the first screen, light hits this, comes out, is in phase, so that the light that hits S1 and S2 are in phase and monochromatic. They act as separate sources themselves, from which we get the interference that occurs on the screen over here. It might look something like this. Found this on the internet, that was pretty cool. You got your first source here, or first slit here, light coming out of there, in phase, monochromatic. Hits the second two slits, they act as separate sources, and from there you get your interference, eventually leading to a pattern here of alternate bright and dark spots, dark areas. For the bright area to occur, we have constructive interference at the very center point. Two waves travel the same distance, they're already in phase. You have constructive interference in bright area on the screen. And also you would have other bright areas. If one wave traveled a multiple number of wavelengths further, so that they again arrive in phase, then you would have constructive interference again and a bright fringe at that point. For the dark areas, the upper wave in this case would travel at least a intermultiple half wavelengths further, so that when you hit the screen, one is going up while the other one's going down. In other words, the trough of the bottom wave overlaps the crest of the upper wave, or vice versa, and you have destructive interference, and a dark fringe occurs. So it might look something like this. Here we got our original source, creating two sources here that are monochromatic and coherent, and they interfere, and we get a pattern of alternating bright and dark areas. Kind of like if you had a bright area and the dark side, you'd have alternating bright, and of course even the dark side was kind of bright. It's kind of reddish though. I'm working here. Working a little bit too hard. Well, in order to have interference, we're going to have that path difference between the two sources. And we will assume that the sources are close enough together and the screen is far enough apart so that effectively these paths from the two sources are essentially parallel. In other words, that slit distance and the screen distance are quite a difference, so that essentially these light rays come out looking parallel. So that the path difference would be this little section right here. If we were to slice this down perpendicular to both parallel lines, then this line below would be this much longer. And if I look at this triangle here, with the hypotenuse being length d, the distance between the slits, and theta is the angle to the fringe, then this path difference from this right triangle would be equal to d sine theta right here. So our path difference is d sine theta. So we would have a bright fringe when that path difference was either 0 or some integral multiple of the wavelength, so that you have constructive interference. So d sine theta equals some integral multiple of the wavelengths where m is equal to 0, 1, plus or minus 1, plus or minus 2, and so forth. M is called the order number, and there's 0, it's the 0th order maximum, and plus or minus 1, the first order maximum, and so forth and so on. This is for constructive interference. What would be the position of those bright fringes? Well, if we look back at this diagram, L being the length to the screen, Y is the distance from the center here to some bright fringe up here at point P. You'll see that the distance Y would be equal to L tangent theta, theta being the angle to that point. But theta is really small. We're looking at a really small diffraction pattern that's really far away from the two sources. So theta is extremely small, and in that approximation, the tangent of theta is approximately equal to the sine of theta. So we can say the sine of theta. Also, the sine of theta from our previous discussion about path length is equal to some integral number of wavelengths, n lambda, divided by d. So making that substitution, the distance to the bright fringe will be equal to the wavelength times length to the screen, divided by the slit distance, times m, where m is equal to some integer, 0, plus or minus 1, plus or minus 2, and so forth. Our assumptions here is that L is much greater than the slit distance, which is true, and the distance between the slits is much greater than the wavelength itself, so we would have them create sources, and that's a pretty good assumption. And our approximation is that theta is small, and therefore the tangent of theta is approximately equal to the sine of theta, which is also a good assumption. For dark fringes, we had enough time. Dark fringes, we've got the path difference would be a half odd half wavelength, so that would have destructive interference. So d sine theta for the dark angle would be an integer multiple of half wavelengths, where m in this case would be 0 plus or minus 1 plus or minus 2. For each dark fringe, we have the central bright fringe, and these would be the dark fringes starting on either side of that central bright fringe. Y position of the dark fringes. Again, since y would be equal to L tangent theta, which is approximately equal to L sine theta, and since sine theta of the dark fringes is equal to m plus 1/2 lambda over d, making a substitution here, we have the position, the actual measured position of the dark fringes is the wavelength times L, length to the screen, over the separation distance of the slits, m plus 1/2, where m is equal to 0, plus or minus 1, plus or minus 2. So these last two are important formulas. In fact, here's a summary. Bright fringes, each bright fringe is the wavelength L over d times m. Dark fringes, I don't know why this turned out K here. I think there's a plus dot 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 here. Just didn't pick up on the new version. The dark fringes is lambda L over d, m plus 1/2. And note that if we were to go from successive bright fringe to successive bright fringe, then we'd be looking at the change, the distance between the fringes. And if we were changing between one fringe and the next, we'd be changing from an integer to the next integer. That difference would be 1. So delta m would be 1. And so for either case, we could solve for the wavelength. The wavelength would be equal to the distance between the slits over the length of the screen times the distance between fringes on the pattern. Whether you're between two bright fringes or two dark fringes, you can measure that distance. And if you know what D was, and if you know what L is, you can measure the wavelength of light. So that's a very nice application. All right, so far we've come up with these. That summary is probably a good summary page with the positions of the bright and dark fringes and the separation distance to figure out the wavelength. Well, that's where you'd be exactly at the bright or dark fringes. But if you're somewhere in between, you can notice that your path difference between the two sources of light would really represent a phase difference between those sources. So in general, if you're right on, the phase difference would be either constructive or destructive interference. But in general, your path difference, sigma, would be equal to d sine theta. Now we could say that that path difference would be the same fraction of the wavelength as your phase difference, phi, is a 2 pi. In other words, if you go one full wavelength, you go one full revolution, if you will, or one full cycle of phase difference of 2 pi. So any kind of path difference that's a fraction of the wavelength would be a fraction of 2 pi in phase. And we could say it this way, that our path difference sigma over the wavelength is equal to our phase difference phi over 2 pi, which I could write as phase difference is equal to 2 pi over lambda times sigma, 2 pi over lambda times d sine theta. I'm headed somewhere with this. That'd be the phase difference between the two sources. Because I want to use it in calculating intensity distribution for these two sources. Consider two interfering waves with a phase difference of phi. Say one wave is E naught sine omega t plus phi, and the other wave is just E naught sine omega t. I just kind of reversed them from the way I had them in your notes. Because it makes it look better when I use this trig identity. Sine A plus sine B equals 2 sine A plus B over 2 times cosine A minus B over 2. So we're going to add these two waves and see what we get. Well, if I plug it into this trig identity, I get a combination of these two waves. The E field at point P is equal to 2 E naught cosine phase difference over 2 sine omega t plus phase over 2. Just plug it into this. And since the intensity is proportional to the amplitude of the electric field squared, we could say that the intensity is proportional to this electric field squared, and so it's proportional to 4 E naught squared cosine squared phi over 2, which is a constant, sine squared omega t plus phi over 2, which is varying with time. Well, if you take the average mean value of sine squared over time, you get 1/2 because it's bounded between 0 and 1. And so if you took the average of that sine squared over time, you would get 1/2. So the average intensity would equal some maximum intensity times the cosine squared of phi over 2. And here I'm kind of making a nice modification. I just put an I max in there before we were just saying it was proportional to. Now I can just say it's equal to some maximum intensity cosine squared phi over 2. Phi is the phase difference, so subbing in for the phase difference, we get that the average intensity is equal to some maximum intensity cosine squared pi times d sine theta over lambda. Or if we use the fact that in the small angle approximation sine theta is equal to y over L, substitute that in, and we get average intensity equals maximum intensity cosine squared pi d lambda L over lambda L times y. So if you know these things, we can get the intensity distribution, and it might look something like this. As a function of d sine theta. So what we're focused on here is how d sine theta relates to lambda. As those become integer multiples, we get our maximum intensities, our fringes, if you will. And here's an equivalent expression down below. So this formula might be useful for some of the problems in this chapter as well. So far we've been looking at interference between two sources. Those sources are coherent and monochromatic. Here's an ingenious way to have one single source stay coherent and monochromatic and have interference. What you could do is have your one source, put it here, some distance away from a mirror, and you have a viewing screen over here. And what it will do is you'll have one part of this light go directly to the screen, another part of this light reflect off this mirror and interfere with that first part of that light. So it's all coming from the same source, but because of this reflection appears to be coming from a secondary source, S prime, behind this mirror. So it's almost like you do have a double source interference pattern at point P. Kind of neat. One thing that would happen, though, is when it reflects off this mirror, this light will invert. They'll have a pi phase difference because of the reflection. and hence the results here on the viewing screen will be exactly reversed from what we had for two sources with no phase reversal.
So would they use something like that in the video projector?
I mean, with a mirror.
I was thinking, inside the projector itself, it probably have like a mirror or something like that.
And have an interference pad.
I don't think so, because there's no possible way that just a single light source could produce that much brightness. Or it would be just very efficient.
Well, you'd want to avoid interference. You want to avoid dark and bright spots. I mean, you might be using mirrors for other reasons, but not for interference. So our equations are reversed from what they were for two single sources that were did not have a phase reversal. That were coherent and monochromatic, or this what's called Lloyd's mirror. So the bright fringes take on the form of what we had for the dark fringes before, and vice versa. Because of this phase change. So if you were to use this, and your real source were some distance away from the mirror, then you would have to calculate your presumed distance between the sources as being twice that distance from the mirror. In other words, since your image is behind the mirror, exactly the same distance that your object is in front of the mirror, then your distance d is twice this distance from the mirror. And so you put that into these formulas. Right. There's a couple problems in the sets that talk about that, and they tell you how far you are away from the mirror, and so you have to just keep in mind when doing that this distance d will be twice that distance. All right, so far so good. I hope. That's one kind of interference. Here's another kind of interference. Thin film. Thin films, you can have phase changes due to reflection, like what we saw from Lloyd's mirror. And in particular, if light were going from a lower index to a higher index, you're going to have a 180-degree phase change upon reflection. We saw this when we were talking about waves in general, way back in Physics 2. If you had, say, a wave on a string and encountered a rigid support, by Newton's third law, for every action there's equal and opposite reaction. So as the wave came in with some amplitude, it would pull on the support, and the support would pull back exactly opposite, so that the result of hitting a rigid support would be that wave would be pulled in exactly the opposite direction, and the reflected wave would be exactly inverted from the incident wave. The same thing would happen as light is approaching from a lower index to a higher index. So it inverts upon reflection, and hence, if you're going from N1 to N2, where N1 is less than N2, you'll have a 180-degree or pi phase reversal of the light. But if you're going from a higher index to a lower index, no phase reversal. The analogy to mechanical waves is if I had a wave on a string and I went to a free support where it's freely ready to go, so that the support is not going to have a reaction force. The wave will come in, it'll move freely along that, and the reflected wave will be not changed from the incident wave. It'll come out the same way as it came in. no phase change upon reflection. That's two things we need to keep in mind when dealing with thin films. Interference effects are commonly observed in thin films. Examples are soap bubbles, oil and water, oxidation layers on antique glass, metal oxide layers on ceramic glazes. And the interference is due to the interaction of the waves reflected from both surfaces of the film. So you're going to have one reflection off the first surface of the film, another reflection off the opposite surface of the film, and interference between those two sources of light. So here are facts for interference. Electromagnetic wave traveling from medium of index N1 toward medium of index N2 undergoes a 180-degree or pi phase change on reflection if index 2 is greater than index 1, and no phase change if index 2 is less than index 1. Keep that in mind. Also, when the light is actually in the medium of a certain index, its wavelength will be reduced by its wavelength in a vacuum divided by that index of that medium. So when it's actually within the medium, its wavelength will be the wavelength in the vacuum divided by n. And I added a third one, which might not be in your notes, but it goes along with these calculations. One reflected wave travels a greater distance than the other reflected wave. So we have a phase change due to travel distance. Phase change due to travel distance. Notice I try to rewrite these things, and less is always more. So I always try to rewrite these things with less words, but sometimes I add things. Here's an example. Here we have a ray that's coming in, encountering the thin film. Encountering surface A, it's going from air to some index of refraction, so it's going from 1 to something that's higher than 1. So it's going to reflect and have a phase change, a pi phase change. Part of it refracts, goes into the substance, traveling with a shorter wavelength, and reflects off this opposite surface here, going from a higher index to a lower index, so no phase change off that surface, comes back through the thickness of that substance, and the two might interfere up here. We have a phase change due to the first reflection, no phase change on the second one, and we also have a phase difference due to the fact that the second path was twice the thickness of this film. Twice was longer path. Here's how it might look. See if I went from air to soap film back to air, so it might be like a soap bubble here. And I have red, green, and blue incident on this soap bubble. That reflection off this bubble would be constructed if it just so happens that the thickness of this soap bubble was, in this sense, I said 3/4 of the wavelength of the green light. In other words, if the green light travels a total distance of 1.5 wavelengths, right, to go there and back again, and then you have a phase reversal of a half wavelength due to the first reflection, that means that the light that goes there and back again will constructively interfere with the light that reflected off the first surface, and hence you would see an intense green light. And all other wavelengths would not interfere. Right? Other wavelengths would not have constructive interference, hence you see green light from white light incident on this soap. Neat. For instance, here's a soap bubble, and you see all sorts of colors because the thickness of this bubble is very thin, but it's changing. So at different points, you have constructive interference of different colors, and hence you get this kind of iridescence of different colors of the rainbow at different thicknesses of the soap bubble. Here's another example. Here's oil on pavement. I think these are two maple leaves over here. You can see because of the thin layer of oil, you're going to have some constructive interference at different colors, and hence you see different colors coming off of this pavement of this situation here. I don't know where this came from, but very colorful. And evidently interference going on here. I think it's some kind of oil again.
Almost looks like a fractal.
It does. It's like a fractal. Probably that kind of mathematics would work on that. Someone told me that hummingbirds have iridescence and that they actually don't have pigments. Who told me that? Because I put that in here. Paul. Oh, butterflies, okay. All right, so you were responsible for me putting this in here because you made me think about that. There's no particular pigment, but it's the interference that you get in order to get the different colors from. And as you move your head, you would get different colors that might go from green, depending on your angle. Yeah. Try moving your head, see what happens. See there. See different colors from moving your head around, but the different iridescence.
I wasn't responsible for that.
No, you weren't. Frankly, I'm a little bit embarrassed by it. It's not a very good sweater. A sweater. Yeah. So, for constructive interference, what we want is the total path difference, which would be 2 times the thickness of the film, to be an integral number of half wavelengths, where the wavelength is the wavelength that it has within the film itself, which would be the wavelength divided by the index of refraction, the wavelength in the vacuum divided by the index of refraction. So it would look like this. That would give us constructive interference for that wavelength. Or simplify it like this. 2 times the index of refraction of that film times the thickness equals an integral number of half wavelengths over here. This takes into account both the difference in optical path length and the 180-degree phase change that occurs on the first surface. And for destructive interference, then we'd want 2 times the index times the thickness of the film equal an integral number of wavelengths, because you're going to have that one phase reversal upon the first reflection, and that will give you your destructive interference. One trough versus one crest. Factors that influence interference. The wavelength of the medium is the wavelength out of the medium divided by the index of refraction of the medium. Possible phase reversals on reflection. Differences in travel distance. These conditions are valid if the medium above the top surface is the same as the medium below the bottom surface. In other words, if I had a soap bubble, it was in air, and I had air above and air below, then this would work. Because you're going to have one phase reversal. But you could put the thin film between two different media. You could have a thin film over something else, and it's possible that you have your lowest index, maybe air, and then you have the film index of refraction, and then the substance below that might even be a higher index than the film. Hence, you're going to have a different situation. You're going to have a phase reversal on your first reflection, and then as it goes through the film and hits the second surface, you'll have a phase reversal there too, because you're going from lower index to higher index on that second surface as well. So you'd have two phase reversals. And in that case, then our conditions for constructive and destructive interference would be reversed. Those formulas would be reversed because we'd have two phase reversals for that situation. So it looks like this. If we have one phase reversal, constructive interference would be dominated by this equation here, and being the index refraction of the film. M is the order number of the interference. Destructive for two phase reversals or no phase reversal, and vice versa for destructive and constructive between 1 and 0 or 2 phase reversals. So what we need to know for film is the thickness, the index of refraction, and whether or not we're going, what are the index of refractions of what we're going to from and what we're going to, so that we know how many phase reversals we have. Here's an example of that latter case. Here I have a film of silicon oxide on silicon to try to minimize possibly reflections off the solar detector. And I'm going from air to a higher index to even higher index. So I'm going to have one phase reversal of the first reflection, another phase reversal of the second reflection. And so if I want to create a destructive interference so that I don't lose this light, then I would change the thickness accordingly to create destructive interference. Here's another example of interference, and you can almost use the same analysis that we just used on film to figure out how this might work. Here we've got a plano convex lens that we're going to place on a flat piece of glass. And if we had light coming in here, going from a higher index to lower index, no phase reversal there, but then it refracts and it hits this glass over here, phase reversal there, so the light might interfere, and one of the reflections has a phase reversal, so that we would actually have a case where if the thickness were correct, we would have interference. The thing is, though, is I put this plano convex lens on this sheet of glass, my thickness is basically changing. And it's very thin down here and then changes with this curvature. So that my interference fringes will change with the thickness of that air gap. Air gap essentially acting as my quote-unquote film. So the result is interference fringes. Particle model of light cannot explain the origin of the rings, so this helps support the wave model of light. The symmetry of Newton's rings can be used to test optical lenses, because this is what you might see. Some ring pattern like this thickness of the air film. And if I were to focus in and look at how good these fringes are in circular nature, that could help me tell how good the lens was. So that would be a nice way to check on the plano convex lens. How good the symmetry of the lens was.
That's the pattern you want when you're grinding your own parabolic lens. That's how you check to see if you got your curve right.
Have you done that?
Yeah,
Okay.
it's not
So
easy.
grind your own lens, then you would check your pattern to see how good it was. In fact, I really want you to focus on this because you can see some inaccuracies here from one point to the other. Focus very clearly on this. Because you will study your physics. You will study your physics.
That's my favorite.
Thank you.
Yeah.
Didn't see that coming, huh? I think I could probably stop there. All right? Unless you want. Oh, let me talk about this real quick. I don't want to detract from the main idea. But CDs and DVDs, since Josh mentioned it. Data stored digitally, a series of ones and zeros read by laser light reflected from a disk. Strong reflections correspond to constructive interference. Those would represent 0. And weak reflections correspond to destructive interference. Those correspond to 1s. So we get a digital readout from the reflected light off of the disk. Now the way to do that is if I have a series of pits and I don't know what you call that, rectangular amplitude here, that if light were to reflect off the pit and off the top here at the same time, you could have interference between the two. Trying to remember which is which. Pit depth is made equal to 1/4 of the wavelength of light. So there'd be a difference in path length of half the wavelength of light. So if you had destructive interference, then you'd be right at the corner of this pit here, and that would correspond to, I forget, was that 1? So destructive interference would be 1, and then as you hit the plateau here, then you'd have constructive interference, and that would be your 0. And it might be based on timing as well. So you get a string of zeros, and then you hit this corner again, get destructive interference between one level and the next, and so forth and so on. So you store binary digits, which would correspond to your data in a binary system. So laser beam hits a rising or falling bump edge. Part of the beam reflects from the top of the bump, part from the lower bump, ensures destructive interference. Bump edges are read as 1s, and the flat bump tops and intervening flat planes are read as 0s. These are binary numbers. And the difference between that and a DVD is the DVD uses shorter wavelengths, and hence you can store more data because you've got much smaller intervals to deal with. So track separation, pit depth, and minimum pit length are all smaller. Hence, you can store 30 times more information than a CD.
How does like a DVD disc work? How does it get the information off the same?
I don't know. Good question. I don't know. I think I did know one time. There's another optical illusion I just had in there.
This website has so many that are really good.
Really? If you focus on it too long, you get a headache. Let's try a couple of problems from chapter 37. Well, that's a better start. Let's just take a look at problem number 1. So a laser beam, wavelength 694 nanometers, is incident on 2 slits 0.1 millimeter apart. Approximately how far apart will the bright interference fringes be on the screen 5 meters from the double slits? The wavelength is 694 nanometers. Slit distance is 0.1 millimeter, or 10 to the minus 4 meters. Length to the screen is 5 meters. And we have that d sine theta equals n lambda for constructive interference. But we could say that sine theta is y over L. So we have d times y over L equals n lambda, or y is equal to m lambda L over d. That would give us the position of all the bright fringes for constructive interference. Well, in this case, the question is, how far apart are those bright interference fringes? So we want to find how far is the spacing between successive bright interference fringes. So we'd want delta y, which would be equal to lambda L over d times delta m for successive interference fringes. But delta m would be what? 1. Because you're going from 4 to 5 or 5 to 6 or whatever. So that's going to be 1. So the change between the distance between 2 fringes would be equal to 6.94 times 10 minus 7 times 5 over 10 minus 4. I get 0.0347 meters. Answer B. Look at problem number 2. Estimate the distance in centimeters between the central bright region and the third dark fringe on a screen 5 meters from 2 double slits, 0.5 millimeters apart, illuminated by 500 nanometer light. Now the position for the dark fringes is equal to L over D n plus 1/2 lambda, where m is equal to 0, plus or minus 1, plus or minus 2, and so forth. So the first dark fringe would be when m is equal to 0, right? And the central bright fringe is when m is 0, but the first dark fringe is m is equal to 0. So for the third dark fringe, that would be corresponding to m equal to 2. And so if we want to find y for that, in this case, y would equal to L, which is 5. D is 0.5 millimeters, so that's going to be 0.5 times 10 minus 3 that in there. 2 plus 1/2 times the wavelength, which is 500 nanometers. Put everything in as it says. And I get 0.0125 meters. About 1 1/4 centimeters. 1.25 centimeters. That actually would be, but that far, which would be significant enough to locate that fringe.
So you couldn't have used -2 there instead of +2? That would give you like -1.5 instead of 2.5.
Would that be the third dark fringe on the other side? Or -2, so you'd go. I guess you'd have to use a -3 on the other side, right? Because 0 would correspond to positive 1/2 wavelength this way. -1 would correspond to a negative half wavelength the other way. So I guess you'd have to use a -3 if you went that direction. Try an intensity problem. Take a look at problem number 7. Two slits are illuminated with green light, wavelength 540 nanometers. The slits are 0.05 millimeters apart, and the distance to the screen is 1.5 meters. At what distance, in millimeters, is the average intensity 50% of the central maximum? Well, there was a formula that we derived for the average intensity. It's equal to I max cosine squared, that's right, pi d lambda L y. That would give us the average intensity for the interference pattern given those variables of distance to the screen, slit width, and wavelength. So in this case, we're told where's the at what distance is the average intensity 50% of the central maximum. So we want all this to equal 0.5, so that the intensity would equal 50% of the maximum intensity. So we got cosine squared of all this, pi d y over lambda L equals 0.5. Take the square root of both sides. Cosine of all that equals the square root of 0.5. Take the inverse cosine of both sides. So we have pi dy over lambda L equals the inverse cosine of the square root of 0.5. And we want to find y. So y is going to equal lambda L over pi times d, inverse cosine of the square root of 0.5. And in this problem, lambda was given as 540 nanometers. Length of the screen was 1.5 meters. slit width was 0.05 millimeters. And when we take that cosine inverse of the square root of 0.5, we want to make sure the calculator is in radians mode. You do all that. Should get this. About 3.92 millimeters would be the distance away from the central maximum, where the intensity would be 50%. Take a look at number 11. In a double slit experiment, the distance between the slits is 0.2 millimeters and the distance to the screen is 100 centimeters. What is the phase difference in degrees between two wavelengths arriving at a 0.5 millimeters above the central maximum if the wavelength is 400 nanometers? Convert your result to an angle between 0 and 360. Well, so the phase difference is to 2 pi, as that path difference is to the wavelength. And that path difference is d sine theta. So we could say that the phase difference is d sine theta times 2 pi over the wavelength. Just kind of have to start there in order to keep it straight. So if I put in, let's see, also sine theta is by the small angle approximation, y over L. So I could still write this as 2 pi d over lambda times y over L. Substitute in for sine theta. And with the values that we have in this problem, that's 2 pi. D was given as 0.2 millimeters. Y is given as 5 millimeters above the central maximum, so Y is 5 millimeters. The wavelength of the light is 400 nanometers. And the length to the screen was given as 100 centimeters or 1 meter. So that would give us a phase difference of 15.71 radians. But they wanted us to convert this answer to an angle between 0 and 360 degrees. So what we need to do is convert radians to how many cycles that would be. 2 pi radians per cycle. And so if I multiply this by, 1 cycle per 2 pi radians. So I divide 15.71 by 2 pi. I get 2.5 cycles, or revolutions, if you will, any way you want to look at it. 2.5 cycle. And so that would be one 360 degrees, another 360 degrees, and then another half cycle, 180 degrees. One way to do that is just lop off the integer part of this. And so our difference is 0.5 cycles. 360 360 degrees per cycle is 180 degrees. That would be our phase thickness. Good. Let's try a thin film prop. Take a look at all kind of related. Take a look at number 19. Monochromatic light, 500 nanometers, incident on a soap bubble, index of refraction of 1.4. How thick is the bubble in nanometers if destructive interference occurs in the reflected light? So we have light coming in on a soap bubble, index 1.4. And we're going from air to bubble to air. So on the first reflection, we're going to have a pi reversal. And on the second reflection, there's going to be no phase change. So we'll have destructive interference if the path length for the two interfering waves is an integral number of wavelengths, because they'll be out of phase due to the reflection on the first surface. So what we want is, if this is the thickness of this film, we want twice that thickness equal an integral number of wavelengths for the wave within the soap bubble. This wavelength is the wave out of the soap bubble divided by the index refraction of this material of the soap. So I can rewrite this as 2nt equals m lambda. Just kind of rederive the formula that we had in the notes. So in this case, we want to find the thickness. So thickness will equal n lambda over 2 times n. Lambda is 500 nanometers. Let's keep it in nanometers. Divided by 2 times 1.4 times m gives us 179 m, where m is equal to, in this case, 1, 2, 3, so forth like that. So the minimum thickness you would have would be when m was equal to 1, which would be 179 nanometers. M equals 1. And then any other thickness, multiples of that, would also have destructive interference in reflected light. more? Enough? One more? Take a look at 21. Thin sheet of plastic, index 1.6, insert between two panes of glass to reduce infrared lambda equal to 700 nanometer losses. What thickness in nanometers is necessary to produce constructive interference in the reflected electromagnetic radiation? There are two panes of glass. Then we have a sheet of plastic. Index of the plastic is 1.6. And assuming that the glass has an index of refraction that's less than 1.6, probably 1.5, like we've had for glass in the past. So we're actually not going to use that index, but we'll just say it's 1.5. So that this index is greater than above and below. So it's almost like the situation of a soap bubble, in essence. So as light were to come in, we have one phase reversal on the first reflection, no phase reversal on the second. And so in order to get constructive interference, we want the path length to be an integral number of half wavelengths. So we'd want, if this were the thickness of the film, 2 times that thickness to equal m plus 1 half times the wavelength within the plastic. So that would be 2 nt will equal m plus 1 half times wavelength. The wavelength within the plastic would be wavelength divided by n, so I brought n over here. So we want to find the thickness to provide constructive interference. So that would be equal to, I should just put the n over there, m plus 1 half lambda over 2n. So that's going to be somewhere nanometers. Let's go with m equal to 0. Let's go for the minimum thickness. So we have 1 half times 700 over 2 times 1.6. We got 109.4 nanometers. So if I put a thin sheet of plastic, 109 nanometers between the 2 panes of glass, I'll have constructive interference of the infrared light. Good start on chapter 37. Well, actually, that is 37. In one day. What about other